Hello, somebody out there? Who, Ned? Ned, you out there?
Check, check.
How's it going, Ned?
Good, how are you?
PH King Wonderful. Oh, Lexi's in. Thought I'd go all out and give you my Indiana Jones hat today.
Love it.
Let's see where I'm at. I gotta figure out where I am at. And so, any questions, Ned? Lexi, you have any questions?
That essay pop quiz,
Ah.
that's due today?
I'm sorry?
Is that due today by 5? Did I read that right?
It says it's due, but if you look at the assignment thing, it goes until July 15th.
Oh, okay, okay.
Do it sometime between now and then, okay?
Yep.
Do you know what it's about? Did you look at it?
I looked at it, yeah. I saw there was 10 long response questions, kinda. Well, respond at the length I feel like that you want type of questions.
Okay,
Short
now,
response.
okay, I don't need to see chat room.
What did I miss on that test? Do you remember?
Uh, beats the hell out of me.
Had to be a sig fig or something.
I'll get it to you on Wednesday.
Mhm.
Let's see. Okay, I got Jake there. I got, who is 17278? Speak now, 17278. Amy Lee, is that you?
Yes.
Okay, no problem. I could freak you all out. Everybody like the essay pop quiz? No?
Yes.
Did anybody not answer it?
There was like one that I was just like, I don't really have an answer to this question. So I think for one, I said I don't really have like a directive response for this, but I tried like explaining like the answer somehow.
What was it?
I don't remember which one it was. Oh, I think it was the book one. I was like, I don't necessarily have a favorite book, but like one that left an impression on me was this.
Okay. Come on, Lexi, you don't think there's real right answers for this, do
Yeah, how do I
Hey,
get 100 on this
I did
assignment?
not
you?
want to underestimate. If I just put one word and then got a bad grade, that's all my fault for underestimating it.
Okay. Let me see. Let me see where I'm at. Is everybody seeing my screen?
Yes.
It says solutions.
Yep.
More importantly, are you seeing the PowerPoint?
No, not yet.
You're just seeing the solution thing, right?
Yeah, I just see the, like, my SPC page.
Now the PowerPoints?
No, still in my courses page.
Okay. I'll stop share. Share screen. How about now?
Yeah, we got that.
All right. Everybody doing okay?
Not that I
Thank
don't like seeing you, but I want to make a motion to make this permanent. I enjoy sitting on my couch.
you. Sorry, can't do. I hate this. I absolutely hate this.
Uh-huh.
So, let me see if I can get. I got Aaron joining us. I really can't stand this very much, but what are you gonna do? The worst part is, I didn't have any air conditioning at home either.
Oh, no.
You guys gotta go to that learning center. The whole wall, the one wall is nothing but windows facing the morning sunlight. So I was sitting there all morning baking. No sympathy? Come on, at least a little sympathy.
Sympathy. I
Mm,
miss it. My dog walked in the room and I had to mute.
Okay. What kind of dog?
I have a Bernedoodle,
A what? A what?
Bernese Mountain Dog and
Oh,
a
those are
mini
cute.
poodle mix. So it's like a hypoallergenic, non-shedding.
Black, brown, and a little bit of brindle on it.
Yep.
My
Sounds
dog's
cute.
just stupid.
What, Lexi?
I said my dog's just stupid. She's like a GSP mixed with like some other like not very intelligent dog.
German
she
short hair
literally
pointer,
has to take-
GSP. German short
She
hair
has to
pointer.
take Yeah, she has to take freaking dog Prozac because she gets so scared she hides in the corner of the room the minute she hears like a big truck or something go by.
You know, I think it has something to do with the kind of breed, because mine's a Greyhound Lab mix and she's skittish as you can't believe.
Yeah, she's just like a very stupidly bred dog. But she's cute when she's tired.
Okay, everybody's seeing the screen, the PowerPoint, right?
Correct.
Okay. Anybody have any objection to the quiz? Not the one that,
The quiz tonight?
no, not the quiz tonight, the essay quiz.
Oh, no.
Surprise you, Aaron?
It's the same thing. I remember it from before.
Yeah. Give me the same answers.
No, I mixed them up and made some shit up this time.
Wonderful. Absolutely wonderful. Yeah, you guys can see me, but I can't see you.
Love it.
Oh, well. I'm sorry about this, but I just wanted to get this chapter. It's, for the most part, it's boring as snot. So I wanted to get it done with while we could. So I'm hoping I have this being recorded. Let's see. No, yep, I think I have it recorded. This is supposed to be recorded. So. Okay,
Says it's recording.
it does? Where?
I see it in the top left. It's a little blinking thing. It
Yep.
says recording.
And it notified me when I came in that we were being recorded.
All right, good,
Yeah, same. It notified me too.
good, good, good. That's fine. It's kind of that way. If you didn't get it, then you'll be able to view the recording. Those of you in the lab, do you understand what's going on with the lab? Aaron, you may be the only one in. Lexi, you're not in the lab, are you?
She's not.
Aaron, you may be the
Sorry,
only
no,
one in
I'm
the lab.
not. My screen glitched. I was trying to hit
Oh,
the
Amy Lee's in
unmute
there
button.
too. Amy Lee or Aaron, do you understand what's going on with the lab?
Yeah, we're just watching Musgrave's video and doing it off of that.
Yeah, I sent you, just make sure that you have the unknown results in there. They were in the email I sent.
Okay.
And make sure that you view the other video, because the post lab is horrible without that other video. It's gonna be horrible anyway, but
All right.
and there's no great loss with that lab. Oh, another thing. Lab wise, guys. How many points past the decimal did I tell you the Buret's read to?
1, but we rounded out to 2.
One, but you rounded out to 2. Read them out to 2 places. And Aaron, I want to see either you or Noah's results, because I thought your results were much tighter than you showed me in the report.
For which one? Antacid?
No, for the standardization of the base. Carter, welcome in.
Oh, how do you want the extra credit? Just bring it on Wednesday or?
Yes. That seems the most logical to me. I'll hand out the test at that point, and actually you guys didn't do that bad on the test. I was kind of happy about it. Average was about a 66, which is par for the course. Anything else, guys? Well, you got a couple minutes here.
The average molarity I got is 0.2232.
But you weren't precise.
We went out 2 decimal places.
No. You weren't precise. Your numbers. You had 2 that were right on, and then you had 2 that were off. I'll talk to
Do
you on
you-
it. I'll talk to you
Okay,
about
yeah.
it on Wednesday.
Yeah.
Anybody have anything? Got 8 people in here, which is probably about 8 more than I expected. Oh, I got more than that. I got a whole bunch of people. I should. Oh. This has got to be Sophia.
Hi.
Would that be the Sophia? Would it
Yes,
be
it is.
in the Cyrillic alphabet?
Yes. Hold on, I'm turning on my video. Hi.
Hi. Everybody okay? Did anybody go on campus today?
Seminole
No.
campus.
I did.
I'm talking about Gibbs. Anybody go
Me.
on Gibbs? Or has anybody heard anything? Is the chilling room fixed or not?
There was still a sign on the door, so I'm assuming not.
All right. We'll have to see what happens on Wednesday. And again, if similar situation happens, we may be doing this again on Wednesday. But as Ned said, Ned would rather be home, sitting on the couch, right, Sophia? Is that the
With
couch
my
you're on?
blankie.
Oh, you're in a blanket too. No pajamas, Sophia?
Well, I'm not gonna show everything.
Got 1 minute to go, guys.
I think
Noah's here.
Trevor's trying to get on.
I got everybody, Jewel just the second time is getting in here. Have him try
Hello?
and load up again.
What's going on? Yeah. Hold on. I'm online right now. I'm trying to get back so I can view it.
Trevor, just try. Ken,
Yeah.
just tell him to try and reload it.
Okay, I'll try.
He
I'll
has
tell
to
him
be
to
on
try to reload
Chrome.
it.
Chrome.
You have to be on Chrome. Oh, okay. Let's see.
Are you in the class now?
Yeah.
Like in the waiting room?
No, like I'm in the class.
Oh, we all hear you.
Ken,
Yeah.
tell him it is being recorded.
It is being recorded. Let's see.
Ken, I just muted you, okay?
Okay.
All right, ladies and gentlemen. If Trevor can get on, Ken, shake your head, yes. Just tell him to keep on trying to get on. I can't control that at this point. All right, ladies.
Xena and Victoria, they're trying to get in. I just told them where the link is.
Thank you. Okay, participants, this is what I want. I'm not getting anybody in here. I got everybody that's in here is in here. I'm not getting any more people in. There's Erica. Okay, guys, we're going to get this started. Okay, can you see the screen that says, let's go this way. Can you see the screen that says objectives?
Yep.
All right, so we're dealing with solutions. This is not the most exciting chapter that we're going to be dealing with. But there are certain things, certain definitions I have to get through. That's one of the reasons why I thought this wouldn't be any real harm doing this through a Zoom meeting. So again, we're going to go through some terms of background. We're going to deal with something called mass percent, but it's something you already know about. We'll deal with the concentration molarity. We'll deal with sample solution preparation. We're going to get into the dilution equation. And finally, we'll deal with stoichiometry. Guys, molarity is moles per liter. So we can use this if we have the volume to get moles of a reagent and apply it into stoichiometry. Okay, Victoria's in here. So solution, quickly. Homogeneous mixture of two substances. One's usually a liquid. Definitions, a solute is the stuff being dissolved. Solvent is the substance being dissolved. Simple enough. Solute is the stuff you pour the water in on top of. Solvent is going to be the water. Now, usually when you have this, Usually the solvent is going to be larger than the solute. Anybody ever have 151 rum? Ken? Shake your head, Ken. Now, when you have 151 rum, that's 151 proof, which means it's 75% alcohol. If you're saying it's 75% alcohol, you're assuming that water is the solvent. So yes, when you're dealing with alcoholic beverages, generally speaking, water is always going to be the solvent. Normally though, whatever is the larger amount is going to be the solvent. Oh, Trevor's finally joining us. Good. Ken, Trevor's in. So you have to understand that these things can be any state of matter. If we have an alloy like a tuba, that is a mixture of tin and zinc to make the brass. I can have a solid and a solid make a solution up. I can have a solid and a liquid like salt water. Or even if I have something like air. Air is a solution of oxygen, carbon dioxide, and a whole bunch of other things that are in with the nitrogen. Nitrogen acts as a solvent there. So I'm having trouble with this. Now, I like to call this the Popeye complex. Does anybody know what Popeye says right before he beats the snot out of Brutus? Anybody ever watch Popeye? Anybody know who I'm talking about?
Yes, I know what you're talking about.
Yes.
But what does Popeye say right before he beats the snot out of Brutus? He says, I can't takes no more. This is what a saturated solution is. A saturated solution is if the solvent cannot dissolve any more solute. Okay? Riddle me this. How can you tell if a solution is saturated? You come across this beaker and you know immediately whether the solution is saturated or not. How do you know? Come on. Somebody guess.
If it's dissolved.
No, I'm just saying you look at a beaker and you can tell immediately whether you know whether that solution is saturated or not.
If
How do you
there's
know?
precipitate in it.
If they're solid, in the solution, then that means that the solution can't takes no more and it is saturated. It is unsaturated if you can add more in it. So if you have a clear solution, you need to interpret that as being that you can add a little more solute to that particular solution. Now, how do you get more in? This
Add
could
more
be a whole lot of
solution.
science. Yes, Aaron,
You add more solution.
but that doesn't make it more concentrated.
No, you
Yes,
just said, how could you get
could
more
add
in?
more liquid. But how do you get more of the solid in the liquid? Come on, you guys.
You
What
heat
you
it
guys
up.
make Kool-Aid? Have you ever made Kool-Aid in your lives?
You add more solid.
You add more solid, Jake?
Yeah.
You stir it and heat it up.
Jake, you know, if you add more solid, that doesn't necessarily mean more of it's going into solution. You could be just making the pile of solid at the bottom bigger. As Aaron said, if you stir it around, you stir that solution around, you can get more of the water in contact with the solute. And if you get more water in contact with the solute, that means it's going to dissolve it more. The other thing is if you add heat. if you add heat, what you do is you get those liquid molecules moving faster. Same thing you do when you stir it. These liquid molecules are moving faster. That means they can get around the solute better, so that we're able to say that we can get more of the solute in there. Now, sometimes there's a solution called a supersaturated solution. Has anybody ever made rock candy? Come on, some brave person.
Yes,
Shout out. Who is that?
me, Trevor.
Trevor, me doesn't work. If
Oh.
you answer me, I can't tell who you are. Thank you.
Trevor, I forgot that I'm like in a Zoom call. Yeah, sorry.
So Trevor, what do you do when you make rock candy?
It's been a while. I don't remember, but I
Okay.
do like remember making it.
Well, basically what you do is you keep on adding more sugar, heating up the solution, adding
Yeah.
more sugar, and keep on adding it until you almost get like a syrup.
Okay.
Then what you've got this pristine solution where you actually do have more solid dissolved in there than the solution can handle. But because you've got this heated up, you got it at the perfect conditions. Now, when you make rock candy, you put a string in there. And what the string does is it kind of destroys the perfect setup, and all the sugar just gloms onto that string.
I remember that part.
So we also have to describe what electrolytes are. We're going to need this for when we deal with solutions that conduct electricity. And that's basically all an electrolyte is. It's a substance, when put in water, conducts electricity. In order to do that, it needs to be ionic and it needs to be fairly soluble. If it's not both of those, then it's not going to conduct the electricity, because we need to get the ions separated so that the charge can be carried from the anode to the cathode. And so basically what happens is we get a process called dissociation. Dissociation is nothing more than breaking the lattice energy of the cation and the anion. So we break that energy, and then we get the water that surrounds them to keep them separated from one another. If they're in this form, then because they're ions, because they're in solution, they can flow from one end of a positive electrode to a negative electrode. And the process of surrounding these individual ions with the water is a process called hydration. And I'm sure you're all excited about this. This particular slide just kind of shows you that you have this crystal formation, and the waters kind of wheedle their way in there with the positive hydrogens attacking the chlorides and the negative oxygen portion of the water attacking the sodiums, which goes to prove something. This is a true altruism in chemistry. You'll hear this described. You're going to hear this given back and forth through organic chemistry. Chemistry is an extremely prejudiced world. They only like their own kind. By this, I mean cations and anions, things that are charged, like to be in a charged solution, which would be the case when you have a polar substance like water. So water being a polar substance, it's charged. So it will like to dissolve ionic compounds and other polar compounds such as sugar. On the other hand, non-polar solvents dissolve non-polar compounds. That's why, here's the trick, guys. Anybody know what napalm is?
It was used in Vietnam, wasn't it?
It's used in Vietnam, and basically it's this it's this gelatin that basically you can throw on somebody lit and it would stay stuck to them. The way you make napalm is you take styrofoam and keep on dissolving it in gasoline until you get this jelly-like substance. But again, styrofoam is nonpolar, gasoline is nonpolar. They dissolve each other. Like dissolves like. So we have to describe solutions not only in terms of what they're composed of, but in terms of their concentration. And basically concentration is nothing more than the amount of solute in a given amount of solvent. We describe it in a couple terms. One is mass percentage. You know mass percentage, guys. We've already discussed that in the last, in the empirical formula section. It's nothing more than part divided by whole. In this particular instance, the part is going to be the solute. The whole is going to be the whole solution. We're going to deal with molarity, which is moles divided by liters. And we're going to deal with another term very briefly called molality, which is basically moles of solute in kilograms of solvent. There are others you're going to need to know, but for right now, this is all we're going to deal with. Sorry, every now and again, I see people popping up. So again, mass percent, you've already done it. We're dealing with a percentage, part divided by the whole times 100. You're going to get the weight of the solute, divide that by the weight of the solution, multiplied by 100%, and you have your mass percentage. Nothing different from what we've done before. And again, remember the solution consists of both the solute and the solvent. So what's the mass percent of a solution made by mixing 33.9 grams of ammonium chloride in 100 grams of water? Work it out, guys. I'm going to go get a calculator and be right back. Any answers for me? Any answers, guys? You have 33.9 grams of ammonium chloride and you're mixing it in 100 grams of water. What's the mass percent?
25.3.
Ned, was that you?
Yeah.
Anybody get an answer other than 25.3? So basically, when we're doing this problem, we're taking a 33.9, dividing it by the weight of the ammonium chloride and the water, 33.9 divided by 133.9. And that ends up being 25.3%. Questions, guys? Are we good with this or do we have to go further? We good?
Good.
You're my designated good person, whoever said that. Now, we could deal with volume percents. What we were talking about were mass percents. We could use volume percents, which is the same thing, only we use volumes instead of masses. Now, something near and dear to your heart, Ken. Ken? Ken, did you,
I think
Fade
you
out-
still muted him from earlier.
did I?
Just scream it at him.
Ask to unmute.
Hello?
Ken,
Hey,
Ken,
How
I
you
know
doing?
this is near and dear to your heart. This used to be a real thing in around West Virginia. God bless that state. West Virginia, when I was 18, I could go into a liquor store and buy whatever hard liquor I wanted to buy. Yet, if I wanted to buy a beer, I could only buy 6% by volume beer. Ken, would that get me
Yes.
drunker than 6% by weight?
yes?
6% volume? I'm going to teach you something here tonight, Ken, okay?
Yeah,
All right. Isn't the volume percent 6 milliliters of ethanol in 100 milliliters of water? Wouldn't that be true?
yeah,
And mass is 6 grams of ethanol in 100 grams of water, right?
right.
So let's think about this, Ken. If ethanol has a density of 0.79 grams per milliliter, I have 4.74 grams of ethanol when I've got 6% by volume, right?
Yeah.
So Ken, do you want 4.74 grams of alcohol or do you want the whole 6 grams?
I want the whole 6 grams.
I kind of thought you'd see it my way. So, ladies and gentlemen, that is just one of the ways you can deal with you have to be careful what you're looking for when you are looking at a particular label. You need to make sure that what they're talking about when they're talking percentages is that it is a weight percentage as opposed to a volume percent, because you're going to get gypped if you don't. So that leads us to our second type of concentration, and that is molarity. I love molarities, guys. Molarities are so much easier to work with than grams. Who's talking?
Sorry, my Alexa went off. I just told her to be quiet. Sorry, I didn't know I was unmuted.
Yenny, what was that?
My Alexa timer went off, so I was just telling her to be quiet. But I didn't know I was unmuted. So anyway.
Burn that witch. So guys, when we're dealing with molarity, we have to understand it's moles of solute divided by liters of solution. That is what molarity is. And I'll be truthful, guys. I had a student of mine, probably about the second time I ever taught intro. And I started to talk about molarity, and this guy came up to me and said, you know, Mr. Popovich, isn't molarity just like the density triangle? And I looked at him and said, that's brilliant. I think I'll steal that. And so we have to use molarity just the same way as we do density. Only in terms of the molarity triangle, we have moles on top. Then we have a line, then we have molarity and liters. So if I have the moles and I have the liters, there's a line between the two. If I have moles and liters and I want the molarity, I divide the moles by the liters. If I have moles and molarity and I want my volume, there's a line between moles and molarity. So I am going to divide my moles by my molarity. If I have my molarity and my liters and I want moles, then I'm going to have to multiply moles by my liters, I get molarity. Are we good with this, ladies and gentlemen?
Yes.
Okay, right hand up to God, guys. I will not use 22.414 when I have a solution problem. 22.414 involves a gas at STP. You cannot have the volume of a solution and multiply it by the gas constant to get moles. You have to have the molarity multiplied by the volume in liters to get moles. Are we clear on that, ladies and gentlemen?
Yes.
Okay, what's the molarity of a 100 milliliter solution containing 15.6 grams of sodium hydroxide? What are we going to have to do first, Jake? Jake, you out there?
Yeah, I'm here.
Look at this problem. What do I need to get?
The moles of the solution.
I need to get the moles in order to get the molarity, right?
Yep.
So what do I have to do with the 15.6 grams?
Divide that by the molecular weight of NaOH.
Absolutely, good. Then, once I get that in moles, all I got to do is change the milliliters to liters, and I will have my divided by my liters. So here I've got 15.6 grams. The molecular weight of sodium hydroxide is 40. So I multiply it by 1 mole over 40, getting 0.390 moles of sodium hydroxide. I then divide that by 100 liters changed into liters, which is 0.1 liters. Guys, you're going to get tired of doing this conversion. All you got to know is that you are moving the decimal point 3.3 places to the left. If you're dividing it by 1,000, you are moving the decimal point 3 places to the left. If you want to go ahead and do that division out, God bless you. I won't even take anything off. So how many moles of HCl are contained in 250 milliliters of a 0.600 molar solution? Yenny. Yenny, you here?
I'm here.
Unmute yourself. Okay. Now, do you remember what I said about the molarity triangle?
I was still copying down the stuff from before, so I did not.
Okay. The molarity, do you see the screen right now?
Mhm.
All right. That means if I want moles, what am I doing to my molarity and liters?
I'm dividing it.
Nope. Are they on the same level?
Oh, I'm multiplying them.
You're going to multiply.
Yeah.
So when I have a volume in milliliters, what do I have to change that into?
Liters.
I have to change that into liters by taking it, multiplying it by 1 liter over 1,000.
Mhm.
Then what am I doing with the liters?
I am multiplying them.
Say it with confidence, Yenny.
I am multiplying them.
You are multiplying them.
Yeah.
So I'm going to take that 250 milliliters, change that into liters by multiplying by 1 liter over 1,000 milliliters. And then I'm going to multiply that by my 0.600 moles per liter. And guys, every time you see a big M, or every time you see something called a molar solution, think to yourself, hey, that really means moles per liter. And maybe that'll help you get these problems out. Are we doing okay, guys?
Yeah.
Anybody confused? Anybody need anything explained further? You see, the problem I'm having right now is I don't get to see those dumb looks you have on your faces when I absolutely stun you. We good, guys?
Good.
Good.
As of right now, yeah.
All right. Now we got to get into learning how to make solutions. Because basically, if you go out as a chemist, literally speaking, for the first 5 years of your life as a chemist, you'll be doing nothing more than making solutions. So you got to learn how to do it. If you're making a, does anybody know what lactate ringers are? You guys are going into the medical field. You don't know what that is? What are those bags that they?
IV solution.
Thank you very much. So don't those have to be a specific concentration?
Yes.
So you got to learn how to do this to make sure that you're not going to zap your patient. So how many grams of iron 3 bromide? Somebody shout out, what's the formula for iron 3 bromide?
Fe. 2 Br3.
Fe what? Fe?
BR3.
Fe Br3. Thank you, Ned. So I have to know this. I have to know the chemical formula because I'm eventually going to have to get moles. And I'm going to have to convert my moles that I get into grams. So I have this problem. It gives me a volume and it gives me a molarity. I can multiply both of them by one another. That will give me moles. Then I've got a chemical formula. I can use that to determine the molecular weight. And then I'm going to multiply my moles by my molar mass. That will give me my particular answer. So I got 750 milliliters. By 1 over 1,000 milliliters, I get 0.7500 liters. I multiply that by my concentration, 1.75 moles per liter. That's going to give me my moles. Iron 3 bromide, FeBr3. I get that molar mass being 295.6. To get my answer, all I have to do is multiply that 295, that should be 295.6, by 1.31 moles, and that will give me my number of grams. Just a typo. Matter of fact, I can fix that right now. Questions, ladies and gentlemen? You have to be able to go from a solution to find out how many grams it took to make that solution. Or if you're given the grams and the liters, you have to figure out what the concentration is. Whoa, that's not what I wanted.
Sorry, I'm still stuck on the whole like mole triangle thing.
Okay,
I still am trying to figure that out. How's that work?
all right. All right. Thank you very much, Lexi. On home, new slide. All right. Lexi, did you understand the density triangle?
No, I had to write it all out.
All right, that's
Like I
fine.
wrote like,
We can write this out.
sorry, I had to mute real quick. I'm not alone.
Okay, Lexi. Molarity is moles per liter. So Lexi, what do you think you have to multiply moles per liter by to get just moles?
You have to multiply the molarity in liters. I'm just confused about the how to find the liters part, I think.
Okay, that's fine. If you have moles and molarity, okay, Lexi, you see what I have up on the screen now?
Yeah.
All right, I have these two terms. I have moles and I have moles per liter. So how am I going to get this to cancel out moles and end up with liters?
Are you dividing the moles and the molarity?
I would be dividing the moles by the, if I take this and divide it by moles per liter. Am I not doing this, Lexi? Crap. Is that not what I'm doing, Lexi?
Mm-hmm.
So that's what I'm saying. If I have the density triangle, which is up here, and I've got moles, line, molarity equals liters, the moles are going to be divided by the molarity. Does that make sense to you now, Lexi?
I was asking about how to get the liters.
How to get the liters?
Yeah, was that moles over molarity?
Okay. Yeah, that's what we just did. Sorry.
Okay, I was just wanting to make sure.
Yeah, because look, Lexi, if I take moles and divide it by moles per liter, that's like saying moles times liters over moles, right?
Mhm.
Okay, who's got the robotic thing on? There's somebody that has something that's I'm hearing in the background.
Yeah, you can try to mute everyone.
What's that?
You can try to mute everyone.
Sounds like an echo.
Could entirely be. Lexi, are you seeing what I'm talking about here?
Yeah, I'm good now.
Any other questions, ladies and gentlemen? All right. We make a solution. We got 25 grams of sodium chloride and 250 milliliters. Joel, you out there, Joel? Renee,
Hello.
hi, Renee. All right, you have 25 grams of sodium chloride in 250 milliliters. The question is, what is the molarity? Okay, Renee, by definition, what is molarity normally? What label over what label?
Moles of the solute over the liters of the solution.
Absolutely. So do we have liters of solution?
Milliliters, but that can be turned. Yeah.
We have milliliters that can be turned. Now, do we have moles of our sodium chloride?
Can also be solved for.
How are you going to do that?
Is that when I'm gonna need the molecular weight for that one?
58.44. That's the molecular weight of sodium chloride.
Okay.
What are you doing, Renee?
Oh, well, did you want me to solve that real quick?
Yeah,
Or are you pulling it up?
nope. I want you to solve it.
Well, the math on that one, it's gonna be 0.428 moles there.
Okay, I'll buy that. Now what are you going to do with that?
Mm,
0.428 moles. What are you going to do?
Oh, you gotta move the decimal place. You had
Okay.
just said, I don't remember the slot. It looks like on the last one, we just moved it to the right one. It's like
No,
100 divided by 1,000.
if you're dividing it by 1,000, you're moving it to the left 3.
Okay,
All right. Renee, take the 250 and divide it by 1,000. What's
okay,
the number?
that's a 0.25.
0.25, yes. So you're going to take the moles, the 0.428, and you're going to divide it by the milliliters. The milliliters turned to liters, which is 0.25, and that gives you 0.107 molar. Eric, are you out there?
Yeah.
Hello.
Hello.
How many grams of sodium chloride would be required to prepare 500 milliliters of a 2.0 molar sodium chloride solution?
So we need liters. So we have the grams of NaCl. So we would divide the grams of NaCl by the molar mass of
All
NaCl.
right, we're in the second one. Second problem, Erica.
Oh, sorry, I was looking at the third one. My bad. Okay.
All right, we'll
For
do
that
the
one-
third. We'll do the third one. You're on a roll. Third one.
Okay, so we would divide 7.81 by the molar mass, and then that would give us the moles. And then from there we would take the moles times the molarity, and then we would get liters.
Nope.
Wait.
Moles not times the molarity.
Oh, divided by, sorry.
Again, you take the 7.81 grams, divide it by the 58.5 grams per mole. That gives you 0.134 moles. Then now you're just simply going to divide that or multiply it by 1 liter over 0.25 moles. That will give you 0.534 liters or 534 milliliters. Are we good, ladies and gentlemen? Natalie, the last problem. The middle
Okay.
one, how many grams of sodium chloride would be required to prepare 500 milliliters of a 2.0 molar solution?
So would you just do 0.5 liters times the 2?
To give you 1, it's 1 mole. Then you have 1 mole. How do you figure out how many grams you need?
Multiply it by the molecular weight over 1 mole.
Absolutely. Moles are moles. If you want to know grams, it doesn't matter whether you got the moles from doing a gas problem, or you got the moles from doing a molarity problem. Moles are moles. Once you have the moles, multiply it by the molecular weight, you've got grams. And that is, again, as you said, Natalie, 0.5 times 2 gives me 1 mole. I just simply multiply that 1 mole by 58.5 grams per mole. This gives me 58.5 grams. That's how many grams of NaCl I need to put in 500 milliliters of solution to get a 2 molar solution. So guys, you're going to be responsible for learning how to make solutions, and you're going to be responsible for having the solutions, determining how many grams of a substance are in it. We good with this part? Somebody give me a thumbs up.
Good.
Thank you. Now, don't even worry about this. We're not going to even bother with this right now. Okay, riddle me this, Trevor. We
Yes.
just said if we have a volume and we have a molarity, we have the number of moles. And is that not true, Trevor?
That's true.
Okay, Trevor. If I add more water in and do not add any more of the solute, have I changed the moles?
Yes, because you diluted it, and then therefore the number of moles decreased since you're adding more.
But Trevor, I'm not taking moles away.
Oh,
I'm not taking moles away. All I'm doing is dumping more water in. Have I changed the amount of moles I have?
so no, you haven't.
Keep on dumping more. Again, Trevor, am I changing it?
You're not changing the amount of moles, no.
So I added this whole bunch of water, this whole bunch of solvent in there, right?
Yeah.
So would you agree that my initial moles equal my final moles?
Yes.
Okay. Then in order to get my initial moles, if I multiply my concentration by my initial concentration by my initial volume, wouldn't I get the initial moles?
Yes, I think so.
If I multiply my final concentration by my final volume, wouldn't I also get my final moles?
Yes.
But they're equal to one another. So if they are equal to one another, can you see that I've developed a new equation? Molarity under initial conditions times the volume initially is going to equal molarity under the final conditions times my final volume. Does that make sense to you, Trevor?
Yes.
Okay, let me see. What is the molarity of a solution that was originally 53 milliliters of a 0.25 molar KCl that's been diluted to 100 milliliters? We could solve this the old way. And by the old way, I mean, we could take that 53 milliliters, divide it by 1,000 milliliters, and multiply it by the concentration. Wouldn't that give us 1.3 times 10 to the minus 2 moles? Anybody have any problem with that? Then to get the new concentration, I would take the moles and divide it by the 100. And that would give me a solution that is 0.13 molar. But I can make that problem so much easier. I have 150 milliliters of a 0.35 molar sodium chloride solution. I boiled it down to 50 milliliters. What is the new concentration? Leandre, do I have you here?
Yes.
Okay, Leandre, did you understand my derivation of M1 V1 equals M2 V2? The molarity under the initial conditions times the volume initially is equal to the molarity final times the volume final. Does that make sense to you, Leandre?
Yes.
What am I going to do with this problem I have here? Do I know what my initial conditions are?
Yes.
What are they?
The initial molarity was 0.350, and then the volume was 150.
So what I'm going to do is I'm going to multiply 150 times 0.350. And that's going to be equal to what, Leandre? What is my new concentration? Sorry, what is my new volume?
52.5.
I don't know, is that the right answer? Nope, not quite. Okay, Leandre. I'm going to end slide and go through. New slide. Okay. You agreed that we had 150 milliliters initially, right? Is that correct, Leandre?
Yes.
And it was at originally 0.350 molarity, correct?
Yes.
All right. Now, the overall problem I'm dealing with is M1 V1 is equal to M2 V2. That's all we're doing. All we're doing is plugging and chugging, Leandre.
Okay.
So I've got an initial volume and initial concentration. What's my new volume?
Uh, 50.
So that's all we got to do. All we have to do is take our initial conditions, initial volume, our initial concentration, make that equal to our new volume and our new concentration. Do you notice I didn't do something here? Can anybody tell why I didn't bother changing to liters?
Because it's the same on both sides.
If I do it to one side, then I have to do it to the other side. That's another reason why this works out a lot better. New slide. Logic question here, guys. Aaron, you're available.
Of course.
Okay. How am I going to solve this, Aaron? A 5.500 molar solution was diluted 4 times. What's the new concentration?
What'd you do? Just divide it by 4?
Practically speaking, yeah. I've got 0.500 times 1 is equal to X times 4. Come up with a volume. Give me a
What, just
volume.
make up in
Give me a volume, Aaron.
100 milliliters.
What's 4 times 100, Aaron?
4,400,000.
Thank you so much. In both cases, you come up with the same answer. We got any questions on this, ladies and gentlemen? Because stoichiometry is about to rear its ugly head. Questions, guys?
So you just picked a random number for the
Yeah.
one?
Yeah.
Okay.
Pick a number.
4.
Oh, come on. I could do 4. You do 500 times 4 is equal to X. You diluted it by 4. That means you got 4 times the volume, right?
Right.
So what's 4 times 4?
16.
You good with it now?
Yeah.
Any questions, anybody? All right. Now, you now have a third tool in your tool belt on how to make moles. You know, if you have grams, you just have to divide by the molecular weight to get moles. If you have liters of a gas, and remember, that is liters of a gas at STP, you can get moles by dividing the volume by 22.414. Same thing if you have concentration. If you have concentration and you have the volume, you can make moles that way. Moles are moles are moles. It doesn't matter how you get them, they're still moles. Treat them the same way. Now, the middle step is always going to be multiplying the unknown moles by the molar ratio. Excuse me. You're multiplying the known number of moles by the molar ratio to get the moles of your unknown solution. Then you have to look at what the final question is in your problem. If you have moles of your unknown and you want grams, then you obviously have to have a chemical formula with which to get the molecular weight. Moles times molecular weight will give you grams of B. If you have moles of B and you want the liters at STP, it first of all has to be at 0 degrees centigrade and 1 atmosphere. So you're going to take your moles, multiply it by 22.414 liters over 1 mole to get your liters at STP. Now, if you have moles of your unknown and you want the concentration, you have to be given the volume of your unknown. If you're given the volume of your unknown, you're going to take your moles, divide it by the volume of your unknown. That will give you your concentration. So you got to look at what the problem is asking you to do. What volume of 0.492 molar HBr will react completely with 25.00 milliliters of 0.540 molar potassium carbonate. So riddle me this, guys. Do I have the means to get moles of either HBr or potassium carbonate?
Potassium carbonate.
How am I going to do that?
Well, you've got the molarity, and then you just multiply the molarity and the volume to give you your moles, or change it to liters first, and then multiply it.
Anybody have an argument there? Okay. Now let's look at the backside of this problem. I want volume. I'm given concentration. What do I need to have if I have concentration and I want volume?
The weight.
Specifically, go beyond weight.
What do you mean? Like how many grams exactly you need of it?
Nope. What I'm asking is, I've got a concentration of HBr, right, Aaron?
Yep.
Okay. I want the volume. Remember the molarity triangle. I have concentration. I want volume. What other number do I need to have to get the volume?
Oh, the moles.
So I'm going to use my volume and concentration of my potassium carbonate to make moles of potassium carbonate. I'm going to use the molar ratio to figure out how much HBr will react with it to get moles of HBr. Then I'm going to take the moles of HBr, divide it by the concentration. That will give me the volume. So I take my milliliters, turn it into liters, multiply it by the concentration. This means I have 0.135 moles of potassium carbonate. Zena, you out there, Zena?
Yes.
Okay, Zena. I have 0.13 moles of potassium carbonate. Zena, you with me?
Yeah.
Okay. Do I have a way, if I have 0.135 moles of potassium carbonate, do I have a way of determining moles of HBr?
Is moles all you have?
That's all I have.
Yeah, I think so.
Okay. Zena,
Yes.
what's the molar ratio between potassium carbonate and HBr?
2 to 1.
So if I have moles of potassium carbonate, what am I going to do with that?
Divide it by 2.
No,
And multiply it by 2. I mean,
I'm going to multiply it by 2 because I've got moles of potassium carbonate. I'm going to multiply it by 2 moles HBr over 1 mole potassium carbonate. And that's going to give me 0.0270 moles of HBr. Now I have my moles of HBr and I have the concentration. Who haven't I bothered here? I got 22 people here. Sophia, I haven't bothered you yet.
I'm here.
Okay, Sophia. I've got now 0.0270 moles of HBr. And I've got my original problem. Can you answer my original problem now?
So we're gonna divide the moles of HBr by the 0.492 molarity of HBr.
That's exactly what we're gonna do. We're gonna take our moles, divide it by my molarity, and this ends up with 0.0549 liters or 54.9 milliliters. Guys, we're working these problems the same way we worked the stoichiometry before. What mass of sodium bromide will react completely with 37.09 milliliters of 0.825 molar lead 2 phosphate? Noah. You there, Noah? Are you asleep, Noah?
I'm here.
Okay. Did that just go crazy? Is my, oh my, damn it. I gotta get the screen back. Okay, I got the screen. You seeing the screen, Noah?
Yeah.
Okay. Do I have a way of getting either moles of lead 2 phosphate or sodium bromide? Do I have a way of doing that?
For the lead 2 phosphate and sodium bromide, let's see here. Yeah, we have a stoichiometric relationship between the lead, what is the PO for?
Phosphate.
Phosphate. Yeah, we got the lead phosphate right here.
But the question I had for you was, do we have a way of making moles of either one of those two things?
Yeah, because we have 37.09 mils of 0.825.
Tell me what I'm doing.
So we need to just get that to a point of moles per liter.
We have that already. No,
Well,
we
yeah,
have,
yeah, we have, sorry, we got 0.825 moles per liter. We got 37.09. Hold on, I need my scratch paper. So if it's equals 0.825 1000. Okay, just give me one more second. 37.09.
guys, when do you think he's gonna notice that I've changed the screen?
I will not notice because I am on a different tab.
Ah, there you go.
I'm guessing that you have the answer up there.
Come on, Noah, what are we doing?
I'm getting back there. So we're gonna multiply the lead phosphate by 1 liter over 1,000 milliliters, and then multiply that by the molarity.
I do that, I got 0.06306 moles of lead phosphate, lead 2 phosphate.
Mm-hmm.
So I've got my moles of lead phosphate. What am I gonna do now, Noah?
So we need to figure out the oh Jesus. My brain's working at half capacity today, Mr. P.
Half of nothing is
Nothing. I know that one.
Noah, what's the molar ratio?
The molar ratio is 6 to 1.
So if I know my moles of lead phosphate, what am I multiplying the moles of lead 2
We're-
phosphate by?
Well, we're multiplying
check,
that by
check,
6.
check.
Okay. So I got my 0.0306 moles of lead 2 phosphate multiplied by 6 moles of sodium bromide
check.
over 1 mole of lead 2 phosphate. That gives me 0.184 moles of sodium bromide. Somebody tell me, what's the question asking me for?
The mass.
So if I have the moles of lead bromide of sodium bromide, how am I going to get the mass from it?
Multiplied by the molecular weight.
This is not as hard as you guys are making it out to be. I got 0.184 moles of sodium bromide. I multiply that by 102.9 grams of sodium bromide over 1 mole. This gives me 18.9 grams. Are these a little harder, or are they making you work a little more? Talk to me. Talk to me, guys. Do we need to see more of these problems?
Bueller.
Sorry, what did you just say?
Bueller.
Yeah, thank you very much. Okay, nice humbling comment. All right. We're gonna do one more at least. I got 13.11 milliliters of a 0.250 molar barium chloride. I react that with 19.80 milliliters of 0.225 molar sodium or silver nitrate. Evie, I haven't bothered you yet today, have I?
You have not, but I'm having a slight issue. So please pick someone else.
Okay. See, that's all it takes.
My cat knocked over my fish tank. That's the problem, but I'm
Oh
fixing it.
gosh.
It's an
Do
issue.
you have to,
but
do you
we're
have to
fixing
feed the cat tonight?
I hope so. I found my fish and he's okay. Just traumatized.
I thought that's why you had a fish tank.
Oh, he's a pretty mustard gas beta.
And wash your mouth out. Carter. Carter, you there? Carter? Okay, let's go with Sophia.
I'm here.
Okay, are you seeing the screen, Sophia?
Yes.
I'm glad you're seeing it because I'm not. Okay. I gotta stop sharing. I gotta get it back there, okay?
Right? That's the screen, right? Well, now I just see you.
Now you see it again, right?
Yeah, I do.
Okay, Sophia. Do you have a way of making moles of barium chloride?
Yes, we're gonna use the volumes times the molarity of BaCl equals to the volume times the molarity of AgNO3.
You can't do that. You can't do that, Sophia.
Well,
What you were quoting was the dilution.
The moles are equal the volume times molarity of AgNO3. To find the mass, we need the moles.
Yes. Yes,
Oh, yeah,
you're absolutely right. But what you're proposing will not work. What you're trying to do is you're trying to use M1V1 equal M2V2, aren't you?
I got confused about that.
Okay.
But we're gonna
You're
use
dealing,
the
basically
volume.
right now, for the rest of you that don't understand why you can't do that, you're basically comparing apples and oranges. You have a solution of barium chloride and you have another solution of AgNO3. So you can't compare them because you don't know that the moles are originally equal to one another. Is that good for you all? Okay, Sophia, do I have you back?
Yes.
Do I have a way of getting moles of barium chloride?
Yes.
Do I have a way of getting moles of silver nitrate?
Yes.
Well, that sounds like I have a way of getting moles of two different reagents. What kind of problem is that?
Double replacement? Is that
No.
what you're asking?
Throw it out to the class, guys. If I have a way of getting moles of each of my reagents, what kind of problem is that?
Limiting reagent.
Thank you very much.
Oh.
So
So you have to
basically,
do twice.
you have to figure out how much silver chloride your barium chloride can make, and you have to figure out how much silver chloride your silver nitrate can make. Whichever one is smaller is the amount of the sodium chloride that you can report out. So Sophia, can you give me one? I don't care barium chloride or sodium or silver nitrate. Can you tell me how to solve for moles of one of those?
Well, is it gonna work the volume times the molarity?
Volume times the molarity will give me moles.
Barium chloride is going to be 13.11 times 0.250.
You got to change. Remember, you have to change the 1311 to liters, though.
Liter.
Okay.
Yeah.
Renee.
Yeah, it's going to be 0.0.
I'll show you that in a second. Renee.
Uh-huh.
How are you going to get moles of silver nitrate?
This isn't the 13.11 divided by 1,000 times 0.225. Is that something different?
No. Silver nitrate.
Oh, I was on the barium.
Yes.
Okay.
Do the same thing, Renee, that you were going
Okay,
to
well
do.
then 19.80 divided by 1,000 and then also times the same molarity, right?
Exactly. So what they both said was you're going to take your milliliters, change the liters, multiply that by your molarity. That way you have the moles of barium chloride. You're going to take your milliliters of silver nitrate, multiply it by 1/1,000 to get the liters, multiply that by the molarity. Now I have moles of silver nitrate. Now I have moles of each. I have to go through the molar ratio. Mariana, you out there?
Yeah.
What is my molar ratio of barium chloride to silver chloride?
1 to 2.
1 to 2. So my moles of barium chloride, am I multiplying it by 2 or dividing by 2?
Multiplying.
Multiplying by 2. So I'm going to take my barium chloride moles and multiply it by 2 moles of silver chloride over 1 mole of barium chloride. Victoria, do I have you out there yet? Victoria?
Yes.
Okay. Can you tell me what the molar ratio between silver chloride and silver nitrate is?
Is it 3 to 2?
No. What's this coefficient in front of silver nitrate?
It's
Are you seeing the screen, Victoria?
yes. Okay, it's 2.
2. What's the coefficient in front of silver chloride?
2. So it's 1-1.
1-1. So now I've got my crap. I have my barium chloride. I'm going to multiply that by 0.00328 times 2/1. And that's going to give me 0.00656. I'm going to compare that to 0.00446 times 2/2. That's going to be 0.00446, which is my limiting reagent, ladies and gentlemen.
AgNO3.
AgNO3. So now all I got to do is multiply that by the molar weight, and I get 0.639. I solved it a different way using this. Oh, no, I did it right. Questions, guys? Was this more the case of a thank you, sir, may I have another, or do we move on to acids and bases? Talk to me. Are you understanding these problems?
We're good.
Yes.
Okay. Okay, stop share. Okay, boom. Boom. Okay, we're going to get into acids and bases. Guys, this is such an important subject that Tro dedicates basically 2 chapters of the book simply to acids and bases. He throws it in on you right now. So we're going to get fairly easy questions. In Chem 2, you're going to get re-exposed to this, and you are going to have much more difficult problems with this. So are you seeing the screen? Are you seeing the screen now?
Yes.
So we're going to deal with some properties of acids and bases, some definitions. We're going to deal with pH conversions, and that's probably where I'm going to be at the end tonight. We're going to deal with the amphoteric nature of some of the acids and bases. We'll deal with titrations, and we are going to talk about equivalent weight. Has anybody ever bitten into a lemon? Leandre, have you ever bitten into a lemon? Jake?
No,
No? You've never bitten into a lemon?
no.
Jake,
I have. Yeah.
what does it taste like?
Shit.
You don't like lemons?
Not straight lemon.
What's it taste like?
Acidic. Bitter.
Bitter.
No, it does not taste bitter.
Sour.
Thank you very much. It tastes sour. So basically, lemons have ascorbic acid in them. So when you bite them, lemons are going to taste sour because of the acid. Now, on the other hand, has anybody been on painkillers for any length of time?
Yes.
Yeah.
What did the narcotics taste like?
Chalk and grossness.
Chalk and grossness. How about bitter? It didn't taste bitter to you?
Not really.
I didn't taste it. I just pounded it.
I worry for you all. Bases taste bitter. If you literally chomp into that morphine-based compound, if you chomp into it, it is very, very bitter because it is basic. Acids, sour. Bases, bitter. Acids, this is a wrong slide. Acids turn litmus red. Bases turn litmus blue. Change it. Acids turn litmus red. Bases turn litmus blue. Acids are corrosive while bases are caustic. Ken. You there, Ken? Give me 5 more minutes, Ken. Trevor, you there?
Yes, I am.
Trevor, I looked up corrosive in the dictionary. Do you know what it said?
Not exactly what it said, but
It said a caustic substance.
okay.
Trevor, I
Yes.
looked up caustic in the dictionary. Do you know what it said?
Did you said toxic or
Caustic.
caustic? No.
Caustic says it's a corrosive substance.
Mhm.
Literally, it's the same definition. For some reason, they call acids corrosive and bases caustic. Each
Okay.
one of them are electrolytes. An
Mhm.
electrolyte means they're ionic compounds that dissolve readily in water
And can produce electricity.
and can produce electricity.
Mhm.
Acids have a pH less than 7. Bases, the pH is greater than 7.
Mhm.
If we are talking inorganic acids are usually gases or liquids. Bases are usually solids. The other thing about bases is they feel slippery. Couple reactions. Acids will react with bases to form a salt and water. Basically, if you have an acid and a base together, put the H of the acid and the OH of the base together to make water. Whatever is less is going to be the salt. If you have an acid reacting with a carbonate, a CO3 compound, what happens is you form carbon dioxide. Basically, in that particular case, you form a salt, carbon dioxide, and water. If you have an acid with an active metal, it will react to make hydrogen gas. Bases, on the other hand, react with acids to form a salt and water. We're going to go whatever acids do, bases do the exact opposite. Bases react with carbon dioxide to make carbonates. And they will react with salts to form insoluble hydroxides. When they were first trying to figure out what acids were, They originally thought it was the oxygen in the compound that gave it the acidic properties. Later on, they kind of figured out it was because of the hydrogen, but they couldn't figure out why something like methane, CH4, something that had a hydrogen, they couldn't figure out why that would not be acidic as well. So they had to finally eventually come down to make some definitions. And Arrhenius was the first to come up with a definition. And he basically said acids produce H+, bases produce OH-. Well, this worked all well and good for a while, but you had some circumstances where the base, like NH4, or I'm sorry, ammonia, NH3, they knew ammonia was a base, but it didn't have any OHs in it. So they had to futz with the definition a little bit. So Bronsted-Lowry said acids donate H+, bases accept H+. Then we came down to the Lewis definition. In the Lewis definition, acids accept an electron pair, bases donate an electron pair. If you are going on to organic chemistry, you will be dealing with Lewis acids and bases almost 100% of the time. But while we're in here, we're just going to use the Bronsted-Lowry. Acids are going to accept an H, acids are going to donate an H, bases are going to accept it. And that kind of like looks like where we're at for the evening. Guys, I don't like doing it this way, but I thought I could get away with doing a Zoom meeting tonight. So that's why I did it. I didn't want to rush. It's kind of like I had permission to drop the class tonight. I had full permission by the department chair. But guys, if I do that, I am cheating you, because if I don't give it to you now, I got to rush it in with other classes. So thank you very much for participating. I know this is not ideal. I really do thank you all. And guys, let's hope that the air conditioning is fixed by Wednesday.
Yes, thank you so much.
No problem.
Thank you, Professor.
What should we do?
What's that, Sophia, for lab?
Yeah, can you give us some information?
No problem. No problem. Guys, if you're in lecture, as far as I know, you can cut loose right now. But if you're in lab, you might want to stick around. I'm going to stop share right now, and I'm going to go and try and pull up the lab course.
So we'll just bring the extra credit for test one next time we have class in person.
Correct, Wednesday. Next time we meet in person with each other, okay?
Okay.
I am not guaranteeing that we won't have another Zoom meeting on Wednesday.
Okay.
Because literally speaking, I just had my air conditioning worked on today. It's been going on and off since Friday. So air conditioning is air conditioning.
Terrible timing during summer.
Well, tell me about it, especially when I couldn't even escape to work.
Yeah.
Okay. All right, everybody that's left, are you just from the lab?
Yeah.
All right. Thank you. All right, we're going to course content. Guys, I hate this lab. I cannot stand this lab because you guys generally don't get good results, and it's It's a futzy lab. All right, now I am in the bulk of the lab. Are you seeing where it says video for the determination of an ionic compound? Are you seeing that, ladies and gentlemen?
Yes.
You're going to go to it and it will pop up. Apparently a girl in a bikini.
An ad.
Sorry. Thank you, S.C. Johnson. Okay, what you're going to see here is you're going to see Dr. Musgrave and Dr. Warden. And, crap, what? No. No.
Hit the back button up at the top. There you go.
Thank you so much. I'm glad somebody knows what the hell they're doing. So basically, he goes through and he shows you what he's doing in the actual experiment. And you will end up getting something like this. I'm just going through this real fast. Just watch the video. You're going to get these precipitation reactions for the cation or the alkaline earth. You have to understand you're being given an unknown. You have a salt that's dissolved in water. The salt consists of a cation, which is an alkaline earth metal, and an anion, which is a halide. So you've basically been given one solution that has two unknowns in it. You have to identify the cation and you have to identify the anion. And what you're going to do is you're going to mix things, or you're going to watch them mix things, and you're going to determine whether or not you get cloudiness. If you get cloudiness, that means you have a precipitation reaction, a positive result. And since not all alkaline earths react the same, you're going to get a series of these reactions in which you are going to get different things reacting with different anions. You're going to look at the overall reactions and you're going to try and match your unknown with the pattern that the known materials have. Do I have any questions on that?
No.
Nope.
Okay. Now, the second half of the equation. What you are doing, you are dissolving your unknowns are already dissolved. You're going to take known materials and you are going to add iodine water, bromine water, and chlorine water to this. If your anion is more active than the diatomic halogen, if your ion is more active than your diatomic halogen, then the anion stays an anion. If your diatomic halogen is more active than your anion, what happens is your diatomic halogen reacts and gives its it gives its electrons. Sorry, hold on a second. What happens is the more active halogen grabs the electrons from the anion, and the diatomic halogen now becomes an anion. The original anion becomes the diatomic halogen. Does that make sense to you guys? I know I totally futzed that.
Sure.
Okay, let me ask you this question. You have chlorine, bromine, and iodine. Those are your three choices. Which one is the most electronegative?
Chlorine.
So chlorine's going to want the electrons more than bromine, more than iodine. Would you all agree with that?
Yes.
So if I put chlorine, Cl2, next to iodide, I minus, chlorine wants the electrons more than the iodide does. So chlorine is going to steal the electrons. When it steals the electrons, it now has a negative charge. It's the anion. The iodine has lost its extra electrons. So now the iodine is neutral. Does that make sense to you guys?
Yes.
Now, when you mix these things in hexanes, what happens is the halogen, the diatomic halogen, extracts into hexanes. When it extracts into the hexanes, it extracts as a different color. You'll see this demonstrated when they do this reaction. So bottom line, you're going to take chlorine ions and you're going to mix it in 3 separate test tubes with chlorine water, bromine water, and iodine water. All 3 of those are Cl2 in water, Br2 in water, I2 in water. So those are going to get mixed with the say the bromide, the Br minus. You're going to mix them. And whichever one of those 2 species is the halogen, diatomic halogen, that will extract into hexanes. Hexanes doesn't mix with water, so you'll get 2 different layers. The hexanes will be on the top. And what happens is when the halogens extract, they extract as a certain color. You're going to be able to look at the color, identify what the halogen is, and then you're going to be able to determine whether or not your substance, your unknown, is more active. You're going to take known materials, known Br minus, known I minus, and known Cl minus. And you're going to react it with known Br2, I2, and Cl2. And you're going to note what colors appear. Based upon the series of colors that appear, you're going to compare that to the unknown that I sent you in the email, the unknown color reactions. And that is going to be based, that is going to what you're going to base your opinion on as to what the anion is. Are you kind of understanding what's going on here? So you're going to have to identify a cation from the precipitation reactions. You're going to have to identify the anion from the extraction into hexanes. So you're going to look at the video to determine what the known samples look like. Do I have any questions, guys?
Basically, we're doing this, we're treating this like an online lab.
Like an online lab, Ken. You're going to
I'm
look
not
at the, go ahead.
Oh, no, we're just basing everything off this video, right? I don't
Yes.
actually need to do any sort of chemical concoctions in my house.
You're not going to do any of the chemical mixing yourself.
Cool. Okay.
Okay.
Now, the post lab is very difficult. Post lab is very difficult. Have I lost the screen on you guys?
No.
No.
All right, so we're going to go back to the module that discusses this experiment. Now, the top video is the one that you'll look to identify your unknown materials. If you scroll down, there is another video here for determining there is another video down there for determining more active and less active. And really and truly, guys, you're going to need to have this video in order to understand what's going on in the post lab. Post lab is very difficult. It gives you a series of simulated colors. It gives you basically letters A- plus B2 makes A2 is green in hexanes. B2 is red in hexanes. C2 is yellow in hexanes. So I mix A- with B2 and I get a red color. B2 already is red. It didn't change. So because it didn't change, I didn't get a reaction. If I didn't get a reaction, this means that C-, which is already ionic, wanted to stay ionic. So therefore, there was no reaction. C- is more active than B2. Does that make sense to you guys? If it doesn't, watch the video. Watch the video. If you don't have, if you have questions, guys, my phone number is still in the syllabus. Give me a call. Okay?
Okay.
But I
thank you.
really think you need to look at this video to understand what's going on in the post lab. Do I have any questions here, guys? Oh, one more thing. You are going, the results section. Results section is going to have very few questions. I think there are like 4 questions. It's an easy lab to fill out. But there is something I need from you. All right. First of all, guys, if your substance is what we're dealing with the solubility of the cations. This has to do with that first part of the experiment. If you get a white solid, that means it doesn't dissolve. What they want is most soluble to least soluble. So if you have all 4 of your little wells that have a white precipitate in it, it's going to be the least soluble because it created the most solid. Does that make sense to you? If you have the more clear solutions, then it is going to be most soluble. Second question, it's going to ask you to rank the active from least active to most active. You know this already. Which one's the most electronegative, guys? You have a choice, chlorine, bromine, and iodine. Which one is the most electronegative?
Chlorine.
So which one's going to want the electrons more?
Both of bromine and iodine.
No.
Oh no, chlorine.
Chlorine's going to want them the most, bromine next, iodine next. So if chlorine wants the electrons, it's going to be more electronegative. So you know the answer to this one straight up. Next question. Don't worry about the unknown. That's an extra 10 points. Do you see it says describe in detail? Ladies and gentlemen, I want specific reactions. My unknown reacted to precipitate with sulfate and oxalate. It did not react with iodate or carbonate. This matched known, and I'm lying about this, magnesium. Therefore, I know my sample, my unknown was magnesium. Do you understand the detail I want in this question, guys? Next one's very easy. Just what is the identity of it? Again, my unknown extracted orange. When I added Br2 to it, it's extracted yellow. When I added Cl2, it extracted purple when I added I2. Therefore, I know that this chloride ion reacted the same way. Therefore, I know this was chloride. Are you understanding the detail I want for this question, ladies and gentlemen? Next, just to ask you what the unknown is, then what's the chemical formula? Just remember, alkaline earths have a +2 charge, halides have a -1. So when you do the chemical formula, just make sure you put a subscript 2 under the halogen. Any other questions, ladies and gentlemen?
This isn't a question, but is there any way that even though it was the lecture recording for the Zoom, we could post it in the lab as well so that all of our partners can see what we just went over?
I'll see what I can do, Amy Lee.
Okay.
I'll see what I can do. Okay? And you won't, the recording won't be immediately out anyway. It takes a while for that thing first of all, I got to figure out how to save it again. Okay?
Cool.
Anything else, ladies and gentlemen?
Yes. Are you gonna check our lab notebooks next time in person, or do you want to
You
start
got a
holding on?
9. I checked it already. It
Okay,
was perfect. Especially yours, Victoria.
Thank you.
Any other questions, ladies and gentlemen?
Everything we need for these answers will be in that video
No.
as far as calculation? No.
Do you remember I sent an email to you telling you about the video, right?
Yeah, I just read about the Zoom. I'll look at the email again. I
All
didn't read
right,
it.
look at the email again.
Okay.
The email has 2 particular paragraphs. One describes what's happening with the cation. One's describing what's happening with the anion. If you don't have it, let me know and I will re-forward it to you, okay?
I don't have that email.
Yes, you do.
No, like I actually don't. I don't see it. Check your spam. No, I am.
Okay. You're gonna make me prove this, aren't you?
Wait.
Sorry, I got to move this silly thing. Submit quiz. Yeah. I didn't answer the submit quiz. Okay. Exit preview. All right, now I gotta figure out. Communicate. Class list. Okay. Nope, it's over here. There it is right there.
Yeah, I didn't get that email either, Professor Fee.
Yeah, the
You-
last one I got from you was on the 10th. I
Yeah,
still don't
I
see it.
didn't receive one as well.
Yeah, I was
Right.
wondering, I'm like off your email list or something.
Yeah.
I don't know what to tell you guys.
I can email you personally, like afterward, just to remind you.
No,
Email them
that's
here.
not gonna do anything for me.
Oh, okay.
Is it the email that says like the laboratory's canceled for this evening, blah, blah, blah?
I believe it is.
I didn't
la-
receive that one at all. So
See, it's
The latest email I have from you is from Friday.
Yeah,
Same.
same. That's the most recent email I have from like the class, like email. For me personally, it was soon, but
did you get the email from the lecture?
No, I had to ask
No.
someone else for that.
I had to ask.
me too.
I don't know what's going on, guys.
Me either.
Everybody should have it now. From me.
Yeah, I just looked under the reply all.
Okay, yeah, I got that one from Aaron.
Yeah, I just copied his email and sent it to everybody. So
Yeah, I got it. Thanks.
Yeah,
Appreciate that.
got it,
Thank you.
Thank you.
Well, I'm more importantly, I'm trying to figure out why this is not, you're not getting it.
how do you send it to all of us?
I go to communicate class list,
And you click the box and then email?
click the box, email.
That's what I just did too.
I got it at 1:32.
Yeah, Ken's been getting them. He's been sending them. It's nice enough to do that.
I got all the emails somehow, so
Okay. That's the list, guys. Is your name on this list?
Let me go check.
Wait, crap. Those of you that did not get it, are you in my, no, everybody's in my lecture. All right. Do me a favor. Somebody look. That's the only way I have a bulk emailing you guys. I'll try and figure it out, guys. Thank you, Ken, for forwarding that to everybody. But I don't know, I really don't know what's going on.
Yeah, it's weird.
I'm sorry, I don't know what's going on. I won't get to it until Wednesday morning or afternoon, because tomorrow I'm in HCC all day.
Okay.
I will look into it because somebody else said something about not getting emails from me.
Yeah.
Sorry.
I know that in one of my other courses, the professor wasn't receiving emails for like a week. She was having a lot of issues like receiving emails. She just wasn't getting them for some reason. So I don't know if that has anything to do with like SPC tech support or something.
Amy Lee, I don't know.
Yeah, I don't know. I'm just letting you know. Maybe it's worth talking to them about it.
That's where I was gonna go with it. Okay. Okay.
Right. Bye.
That's it, guys. Thank you very much, Ken. Thank you again.
Thank you. Bye-bye.
Bye.
Thank you.
Bye.
Thank you.
I hope we don't do this on Wednesday.
I hope not.
Thank you.
Bye. I stay here till you all go. That way I know who's cutting out on me.
Peace out, everybody.
Hey, Noah, don't leave yet.
Okay.
All right, so do you want to meet, Mr. P, you want to meet with me and Noah? Because our results should be
Oh.
the same, and
I don't know, guys. I don't know what. Let's see.
because he wasn't.
Let
he
me, one
wasn't in the
second, guys, okay?
Yeah.
Okay. Renee's finally left. I got. Ahmed finally left. I don't know what happened when I did, you remember I did the calculations with you real quick. I
Yeah.
said, oh, you guys are dead on. Remember that?
Yeah.
Mhm.
I don't know what happened, but your results were not nearly as good as I calculated. I don't know whether I did it too quick and I made a mistake. I don't know. But I'd like, what it's all it is I just want to see if I made a mistake or if you guys made a mistake. I'm trying to
Okay.
correct the problem is what I'm doing.
Okay.
So I just want to see your results on Wednesday or when next time we meet. That's all.
Okay.
All right.
All right. Sounds good.
Take care, guys.
All right,
You too, Miss
thank you.
P.